Hello, everyone. My name is Weijian, and I'm a machine learning engineer. So I'm sort of like sitting in between data scientist and engineering. So like my talk is actually on how we can build a reliable and scalable AI system. So just focus on, from the engineering perspective, how can we make sure the system is not just interesting or providing accurate result, but can be used for large-scale systems. So before I go to the slides, actually I want to make a very bold statement. And the statement is, I do very much believe that a well-designed AI system can outperform almost all human beings in decision-making. And the reason they can do that is not necessarily because they are very smart. The reason they can do that is us, as a human, we are actually flawed. And we are, so from the technical term from this paper, or from this book, is we are noisy. And so our decision is kind of deeply depends on what we eat in the morning or what the weather look like. So those kind of things actually have a subtle effect on human making decisions, but the machine can do much better. So from an insurance perspective, this means I do believe pretty much everything from pricing, from fraud, to claim process that could all be done by AI systems. So which will be talking, that will be the last point of my presentation. So my talk will be sort of structured in this way. So I want to start by talking about some considerations with AI system in production. And then I will talk about what we do at Marshmallow. And there's two interesting things we developed at Marshmallow. One is called the feature store, it's machine learning feature store. And also we're using SageMaker, is an Amazon-based system to build automatic model training and deployment process. And in the end, I will touch about what I think is kind of the future of AI systems. So at the beginning, so actually I want to start with a very kind of example. It's a very simple example. So suppose we're building an AI system, we're using the rooster to predict the sunrise. So as a common fact, as a well-known fact, is basically the rooster will crow before the sunrise every morning. And if you're building a machine learning system, basically saying that I'm using the rooster as a variable, we want to use that to predict the sunrise, you got a very accurate result. And you will deploy that system into production is fantastic, and everything's working so well, and you're very happy. Your manager is very happy, until one day, like a butcher come in and kill the rooster. Then suddenly, you don't have that variable anymore, and your system basically saying, okay, I didn't hurt anything, so that means the sun will never rise. Of course, you know that's not the truth. What is here is basically people sometimes confuse between correlation and causation. And the correlation does not imply causation. And my main thing, like we do in machine learning, we're taking the features and we're trying to using that to predict a target. What we're actually doing is the correlation part. And the correlation, that means some data can go missing, actually from the previous speaker's point. Some data can go missing. And the experience has shown the external world is really stable, is always changing. And you may do some unit testing, you may do some integration testing, but that may not be sufficient to prove the system is actually working as intended. A good AI system, I believe, should handle uncertainties that including missing data, edge cases, that kind of thing. This is my first point. My second point is about what's important thing is not about how accurate your model is today, but how fast you can tune the model to meet new requirements. Because the world is always changing, and you cannot assume the model is working today will always be that good for tomorrow. And this is actually from a talk by David Telby on why machine learning models crash and burn in production and what to do about it. So this graph shows it depends on the problem, the model, sort of how fast we need to changing to retrain the model is actually depends on the problem. So from the never changing side, you got face recognition, voices, and those things like common human features that things don't really change, so that's okay. But in our case, in insurance, we're actually pretty much close to the always changing side. So you got fraud and you got pricing, and that's actually very interactive. So you price someone this way, And the person may react in a different way and causing you the model to change your model, you have to reprice it again. So this is kind of interactive game that we have to basically always changing the model, and retraining the model may not be sufficient. And my last point is actually the machine learning code is actually just a very small part of AI system. And you have to take account of other things, including like the monitoring system, including how the infrastructure is done, and how to, how the hardware is actually managed. So all of those things is contributed to the whole of a machine learning system. So we cannot just changing the machine learning code to deploy it in production, but we have to take account of thinking about everything that relates to the machine learning code. So that's the consideration part. So the second part, I want to talk about what we're actually doing at Marshmallow that trying to tackle those problems. The first thing is called the feature store. So the idea is actually quite simple. It's kind of like we want to, you train a model, you have to have features. So we want to have a single source of truth that holding pretty much all the features together. And it's work like this. So during the training pipeline, so it's like offline training, you got the data coming in from maybe some data lake, and then the data coming in through the feature store. The feature store will load in the data and enrich it, sort of like make the data much more refined, and then send the data into a machine learning model, and the machine learning model will train the model, train the data. And then during inference time, you basically got the real-time data coming in, and the feature store will need to handle the real-time data, sort of doing the conversion of the real-time data, and then send it to the machine learning model to get a result, so the API endpoint to get a result coming out. So we kind of thinking about, okay, this is the thing we want to build. How we can sort of like thinking, what is the sort of the fundamental requirement if we want to build this thing in-house? And the approach we take is sort of break it down into smaller pieces, like Legos. And those Legos is actually quite easy to build, and we're basically building those kind of 3 Legos. So the first part is you need some kind of a data loader. So the job of the data loader is during the training part, you load like the vast majority of data from the data lake to the data pipeline. And then you need a data parser. The data parser is used in inference time to pass the JSON data into some kind of well-defined format. And the final part is you need a data enricher, which basically converted the root feature into enriched features. So this would actually look like during the training pipeline. So you basically taking you need to use the data loader to load data, and you pass that to the data enricher, which enrich data, and then you're using the enriched data to train your model. And during inference time, you're using the data parser to pass the data, and then the pass data will be getting enriched again. So you can see the data enricher is shared by both the training process and the inference time. So we're basically building these 3 components and allow the data scientists to using this new infrastructure to make the training and inference process much more easier. So I can give you like what is coming from past compared to the past compared to the present. So in the past, the engineers need to provide the transformed, the enriched feature to the machine learning model. And whenever there is like a feature change or something, the data scientist has to inform the engineers if there's any updates needed. And which is not ideal, because you got cross-team, different communication channels, which will slow things down. The best approach is actually to give the data scientist the full power to handle the entire data pipeline. So basically, by using the feature store, the engineers only need to providing raw data. The raw data never changed. So whenever the data scientist is making some changes, they do not need to talk to the engineers. They will make the changes inside the feature store, and the data scientist is responsible to handle any kind of missing data or education, that kind of thing. Because the reason they can handle it is they are the ones who design the machine learning system. They know it the best. So it's rather than ask them to handle it, it's much better to just talk to another different engineers to handle the problem. So that's the first part of our solution. The second part is we're actually utilizing Amazon SageMaker to build a model training and deployment process. So from a kind of engineering background, I like to think in abstractions. What is the training of abstraction? Essentially, what you do during training is basically you need some computation resources, right? So you're basically loading the training code, and you need either a Docker image or some kinds of environment which basically tracking of like your Python version, the package dependency, all those kind of things. And you basically run your training script in the computational resources. And basically the output will be some kinds of training model. It will be like some pickle file, some binary file, and you save that data somewhere. It could be in S3 or your local machine. So this will sort of define the training abstraction. So during model serving, you also need some computation resources. And the difference is actually, you can see the model is loaded in reverse order. So you need to load the model inside the training, inside the computational resources. And you're using Docker image or some other things to make sure the environment is stable, is standardized. And this will be sort of like this kind of standard called endpoint, like API endpoint, which will talking to your main service. So the thing is like this thing is very standard, right? So like you cannot ask like a data scientist, you have to redo this like this kind of abstraction every time. They have to do some like fast API or some Flask app. They do not need to do that every time. So this is just abstraction. So we can basically utilizing like SageMaker or some other tools like for example Kubeflow doing something very similar. So we can building this abstraction to allow the data scientists to just focus on building writing the training script. That's the only thing they need to do. They write the training script, everything else is completely all automated and is actually production ready. Another cool thing is actually we can serving multi-models at the same time. I do believe this is very powerful. You think about like you want to like having one model running in live state, like your main service talking to that, you're getting a result in real time. And you want some kind of challenger models running in parallel, like in shadow mode. So you basically want to check, okay, what sort of like asking the what if question. What if actually I'm using a different model? I sort of like changing the parameters slightly. Will the result be different or it's actually be better? So you want to constantly checking that. And basically our infrastructure allow the data scientists to do that. And the cool thing is only the live model is actually getting the result synchronously, and all the other models getting a result asynchronously, so we won't have any performance issues. So we also utilizing a thing called Terraform. So if you're in engineering, you probably know this. So we're using Terraform to basically standardizing the CI, so continuous integration and continuous development process. So the data scientists no longer need to have to do some coding and do some messy coding and anything. So everything is standardized, so they can just deploy the model immediately into production. So I also want to show this diagram, which is sort of like what we do differently from the past to the present. So in the past, the data science need basically train the model locally, and they need to manually upload the training model into some S3 bucket, and they have to inform the engineers if there's any feature changes. So now, by using this new approach, they're basically training the model completely on the cloud, and we have the CI/CD process for deploying and updating new models. And the cool thing is we actually can deploy multiple models in parallel without impacting the performance of the main service. That's the second part of my presentation. So my last point is just thinking about what I think the future of AI system will look like. So actually I will be joining the panel discussion tomorrow, which is sort of like talking about the future of AI in insurance, so it's kind of a related topic. This diagram actually shows what is already happening in Marshmallow. So we currently have a a machine learning system, sorry, a machine learning model, which the single job is to do some kind of feature prediction, because we don't get that feature in real time. So we have some model trying to generate the predicted features, and we use that predicted features in both our pricing model and also our fraud model. So that feature is utilized in both systems, and it's sort of working like this. And you got the pricing model will return the predicted price, and the fraud model will return the predicted fraud price. So you can see it's kind of a little bit complex. So you can already see the model dependencies in this diagram. So what I believe in the future is the AI system will be more complex than what we have now. And the system will not just working by itself, they will actually sort of talking to each other. And also there will be far more complex dependencies between AI systems. So essentially we have like a swarm of AI systems that are working together. And you think about it from engineering perspective, we have to building the right infrastructure to allow that to happen. And I think the approach we're taking, it's the right approach. So to summarize, to wrap up everything, we're basically like live averaging the machine learning features of which we build in-house, and also the SageMaker-based the training deploy process to allow data scientists to own the whole data science lifecycle and building reliable and scalable AI system. So that's the end of my presentation. Thank you.